Hello friends, welcome back. In last lectures we discussed some mathematical models. First of all we discuss lake pollution model, then drug assimilation model into the bloodstreams. After that we discuss alcohol model, consumption of alcohol model in body. Uh, then we come to this model and the title for this lecture is Models of Single Populations. Simply, this is the population model, and we have already some idea about this type of models. And there is a only single type of population which we have to discuss. And in particular, we will discuss uh, model which shows the exponential growth. So initially, we model exponential growth. So actually, there are different types of models for population growth, but there are some cases where the populations grow exponentially. Then first of all, we discuss this type of model. So we begin by developing a very simple mathematical model which describes the growth of population. A very simple model which describes the growth of the population. So that's clear. So this population may be the human population or any vectorial population or population of any species. So what will be the compartmental diagram for this one? So this is the diagram for this model. So this is a simple model diagram. It means suppose this is our population, and this population may be of a any geographical region which we have to consider. It may be a city, it may be a village, it may be a town, it may be a country, or it may be a whole world. So, so they have explained that the compartment may represent any world, town, organization, or any ocean, etc. Means in which we have to consider the dynamics of the population. And this is the incoming rate, and this is the out rate. So incoming rate means treat as the birth, and the out rate may be considered as the deaths in that population. And this is the uh, normal nomenclature in any uh, dynamics. If we consider in terms of population, then incoming rate is known as the birth, and outgoing rate is known as the death. So if xt is a variable which represents the population at time t in this compartment, right? What is the xt? Xt is the population size, right? Population or population size at any time t. Then what will be the our model? Simple model. Because if we use the mass action law, or if we write down compartmental balancing in terms of word equations. So that is given by this. Means the rate of change of the population size means at the rate at which the population will change is nothing else the rate of the birth minus rate of the death. That's clear. This is just similar to the previous case. In the case of lake pollution model or whatever model we have already discussed, same, this is similar to this one. Means what will be the change in the concentration here? Because here concentration is not there is the population, concentration is replaced by the population. So effective population rate is measured by uh, this is incoming rate minus outcome. So population means rate of birth minus rate of the death. So this is the rate of change of the population size, net rate. So this is our basic idea behind this. So there are some assumptions when we develop a model. There will be some assumptions. So what are the assumptions? Means first assumption is that we are dealing with large population, so that we can ignore the random fluctuations between individuals. Actually, there are two types of modeling. One is known as the deterministic modeling, and other one is the stochastic. So this type of modeling comes under the deterministic modeling. Actually, because we are assuming that okay, here population is very large. If population is very large, then we can treat each individual uh, in same manner. Means each individual can produce or means death in that population are the same. And if population is small, then random fluctuations will be more in that population. So then we will prefer the stochastic modeling, that modeling which is based on the probability. But there is no probability, there is some certainty in our model, and this type of model is known as the deterministic model. So mainly deterministic model are useful when population is large, and we prefer the stochastic modeling where the population is small. So we treat each individual as a being identical. So this is the main assumptions in this our model. So it is again written, thus we assume that each individual in the population has an equal chance of giving birth, and we also assume that each individual has an equal chance of dying within a given time interval. Right? Means we are neglecting the fluctuations between the individuals. That's clear. So this is our assumptions during when we developing the model. So now we discuss what are the rates. So suppose we consider two types of rate. One is the beta, one is the alpha. So what is the beta? Beta is the per capita birth rate. Per capita means per individual. So this is the birth rate which is produced by a single individual per unit time. Time may be in month, it may be year, whatever. It depends upon your question, it depends upon your situation. If you consider the population of human population, then time may be in month or year. But if you consider the population of a bacteria, then it may be time, or that time may be in seconds or hours or minutes. So it depends upon the question and nature of problem. So what is the beta? Beta is the birth rate, and what is the alpha? Alpha is the death rate. That's clear? Per capita per time. So simply you can say in this model, what is the beta? Beta is this rate. Beta is here. And what is the alpha? Alpha is here. Means individuals are coming at the beta rate and individuals are going out from this world population at the alpha rate. That's clear. So now these rates are given as per capita. Per capita means per individual. So now these are some values are given which are estimated by different scientists for different geographical regions. So now we build our model, and first assumptions we have already discussed. So there are four assumptions we have already discussed. The population are sufficiently large. If population is sufficiently large, so that we can ignore the differences between the individuals. And second assumption is that we assume that births and deaths are continuous in time. That's clear because we are dealing with the the differential equations, and these differential equations are assuming these variables are continuous. Otherwise, if they are not continuous, then derivative for these variables will not exist. That's clear. So we assume that per capita birth and death rates are constant in time. Next assumption is that beta and alpha are the constant, because it may be vary with respect to time, but we are not taking as these parameters as a variable with respect to time. They will remain the constant. And third one, in model we ignore the immigration and migration, so which can be included later. So at present level we are not considering the immigration and migration of the uh, population in the compartment. So these are the four assumptions. Means population is very large, birth and death rate are continuous in times, and these rates are constant, and we are ignoring the immigration and migration. So then what will be the mathematical framework with respect to our uh, model diagram? Because what will be the rate of birth, total effective rate? Because this beta was the number of, yeah, it was the rate, birth rate. Which type of birth rate? This is due to only one individual. Okay, this was the due to one individual. So what will be the effective rate? Effective rate will be the birth rate, which is, yeah, number of births which are produced by a single individual. Then what will be the total birth in the population? So total birth will be beta multiplied by the total population in the compartment. And what is the total population? X at any time t. Similarly, if alpha is a per capita death rate, then what will be the total death rate in your population? So that will be alpha multiplied by the total population, because these are due to one individual. These rates are due to the one individual. Okay, per capita per unit time. So if you multiply by the total population, then you will get the total births, and you will get the total death in that population. Then what will be the effective population or rate of change of the population at any particular time? That is given by the rate of the birth, means number of births at any time t, and minus that death of in the death in the population at that time t. So nothing else. If you take beta x minus alpha x, then it will becomes, if you take x common, then it will become beta minus alpha x. So we will say, so you can write it as dx over dt is equal to Rx. And what is the R here? R is equal to beta minus alpha. It's clear. So what is the R here? So this R is nothing else. This is the beta minus alpha. So beta is the birth rate per capita, alpha is the death rate per capita. So this differential equation is known as the population growth model, where this R is known as the growth rate or reproduction rate of the population. So you can see we have already discussed this type of model in previous theory classes, and we have already solved this type of differential equation. And you can check if R is positive. If R is positive means beta is greater than alpha. R is possible. R will be the positive if beta is greater than alpha. If beta is greater than alpha means birth rate is greater than the death rate. Then that describes the growth exponential. But if the case is that, okay, R is negative only when beta is less compared to the alpha. Means birth rate is less in comparison to the death rate. then that will represent the exponential decay. That's clear. If it may be the case as well, if beta is equal to 0, if beta is equal to 0 means there is no birth rate, there is no birth in the population, but there is only death, then that is also minus alpha, that will be the negative, then it will represent the decay. And if there is no death, means alpha is 0, then in that case beta is positive, because alpha and beta both are taken as the positive, right? So if beta is positive, then it will represent the exponential growth. So what will be the solution of this model? So solution of this model is this one. We have already discussed this type of differential equation. This is a first order separable differential equation. For simply, I have solved it so you can see it. It is very easy. So you can write it as dx over dt is equal to rx. So you can separate this one, and if you integrate with respect to t both side, then it will become the log x equal to rt plus c1, because log cannot be negative, but here is the population and population will be always positive, so there is no meaning to write down this mode. So using the initial conditions, if initial condition is given, the population at time t is equal to 0 is given as x naught, then if you use this condition, then c1 will be the ln x naught. If you put the value of this one, then the solution will become x is equal to x naught e to the power rt. So this is given as same as this one, where a is find out the x naught using the initial condition. So this is our solution. So this is the solution, xt is equal to x naught e to the power rt. That's clear. So this describe exponential growth or decay depending upon the sign of r. We have already discussed it. Now we interpret some parameters. So what is the alpha actually? Alpha can be estimate the reciprocal of average life acceptance. If you want to find out the alpha, this is nothing else. What is the average life of species? If you take the reciprocal of that one, then you will get the death rate. And it is easy to find out. How will you find out the number of death in the time interval? What will be the time interval del t? The total death will be, this is the rate per capita, so the whole death will be alpha and x, and what will be the total time period is del t. If you multiply, then you will get the number of death in time interval del t. That's clear. So if we want to find out, okay, what is the t1 is the average acceptancy of the of that species, then if you take xt is equal to x naught, means you have to find out uh, x means population at time t is equal to x naught. If you want to find out, so if you put number of deaths in time interval is equal to x naught, means initially there are x naught in the population, and all the members, yeah, all the individuals will become dead, and you have to find out that time. So if you put x is equal to x naught, means uh, there is no one will be in population, all will become die, then if that can be written as this equivalent to this one, if you put x is equal to x naught, and if you cancel out, then you will get the alpha is equal to 1 by t. So this is the main formula. Whenever it is not given alpha is what is this, just you have given the life expectancy, then you can find out the value of alpha. That's clear. Because for example, suppose a mosquito lifespan is uh, normally 7 days. Suppose we assume 7 days. Okay, then what will be the death rate for mosquitoes? 1/7. Okay, so it is not 7 is confirmed. There is some range actually, 1/7 to 7 to 14 days. Normally a mosquito time span is of his life is 7 to 14 days, then there will be range of for alpha 1 by 14 to 1 by 7. So similarly, you can find out for human as well, because what is the life expectancy for human? That is 7 to 80 years. So if you take the reciprocal of this one, then you will get the range for alpha. So this is a simple example in which they have uh, asked to uh, find the expression for time. Means you have to find out the time when the population will become double in size. So what was the population? Suppose we represent xt is a population at time t, then we have to find out this capital T. Means suppose with that time is capital T, which takes to be double, which takes the time to be double of the population. So that means xt plus t will become the 2xt. Then we have to find out this t. And what was the expression for xt? So we have already solved the differential equation. So what is the expression for xt in solution? If that follow that model, then xt will be x naught e to the power xt, this one, right? And if you put the value of t plus capital T, then that will be the x naught e to the power rt plus t, and that is nothing else. This is equal to the 2. So x naught will be cancel out. Then you can find out the value of capital T, and capital T will be in terms of this one. So capital T is the ln 2 by r. Means actually it depends upon the rate, growth rate. Means when it will take time to be double, it depends upon the growth rate. That's clear. If you can check if r is 0, if r is 0 means that r 0 when r will be 0. If alpha and beta both are the same, they both are the same, then that quantity will goes to the infinity. Means it will take the infinite time to be double. Means if alpha is equal to beta, means population will remain constant. Okay, so in that case, population is not changing with respect to time, right? So they have discussed some examples. You can find out in this exercise easily. Just put the values and you can find out these means when the population will become the 5 times, 10 times, or etc. It's clear. So we have already discussed this type of model. Now next we discuss the real. What is the real scenario? So, so what is the real scenario? We discuss. Actually, this is the actual graph of the any species. You can find out what is not actual. We read out. This is the difference between trend of the experimental data of a yeast culture, right, and the continuous growth model prediction over time t. So actually, this is the exponential growth which is given by the model. This is given by the model. Which model? Exponential model, which we have already discussed. This is the experimental work, right? So this is given by the model, but actually growth is this. This is the actual growth. But our model experiment by the estimation by the model is given by this. So there is a very variance between these two curves, right? Because up to here it is all right, but after this time period, it is going to like this and it is going to like this. So means if we want to estimate the or if we want to prediction more accurately, then we have to implement something else. So what is this? After some time, the population is going to at a constant rate, right? So this is the natural phenomena. Okay, a population never goes increase exponentially. Right? Somewhere it will stop and will start remains the constant. So to apply this concept, uh, we discuss this concept, which is known as the density dependent, right? So we have already seen that if population are observed over long period, they often appears to reach a limit or to stabilize. Right? So we modify the exponential growth model of the previous model section to the account of competition or limited resources. So what is the meaning of competition or limited resources? Means why this population remains constant? Because always a geographical region or any medium or any environment has its carrying capacity, has its carrying capacity. So what is the carrying capacity? This is the number is called the carrying capacity. So what is this? This in principle, a given environment can support only a limited number of individuals. That's right. So this is known as the restriction on the resources or limited resources are available. So due to the limitation of the resources, always an environment having a carrying capacity means environment only support uh, or can provide the facilities up to that carrying capacity. And in biological literature, it is represented by the capital K. That's clear. So technically, we can say this is the population size or density for which the per capita birth rate is equal to the per capita death. Means what is this? This is the population size. This is the population size where the birth rate and death rate will become the same. When the birth rate and death rate will become the same means then population will remains the constant in the environment. Means after reaching at this level there will be no population growth. That's clear. So some scientists also has estimate what is the capacity of the earth in terms of number of population for humans. If the number of humans will reach that population, then automatically uh, death rate will become equal to the birth rate. So how we will incorporate this concept in our mathematical model? So in our mathematical model, we consider this was our equation. So in previous case we discussed what was the birth rate. Birth rate was total effective birth rate was the beta 2x, right? So uh, and what was the death rate? Death rate was this one, gamma, not this one. This was the death rate was the alpha and xt. This was the effective death rate. That's right, alpha xt. So now what will be the scenario in this case? We consider means now if population is not depending only the x, right? Uh, as well as there are some unnatural phenomena are there due to some additional deaths are occurring. Means institute of assuming at a constant per capita death rate. Means previously we considered this alpha was constant, and if you multiply that here, so that will remains the constant death rate, which depends only on this one. But here we allow the per capita death rate to increase as the population increases. Right. In the previous case, this was the fixed. This alpha was the fixed for each time. But here we are considering that there is not only alpha, there is some type of function which depends upon the population size. Means if the population in the environment is increasing, then the death rate will also increase. That's clear. So in that case, we consider this type of linear function. Linear function means in previous case it was the only alpha, right? But in this case, this alpha is replaced by alpha plus gamma x. In the previous case, it was the fixed for all time t, but here it is changing with respect to time t. And what is the time t? With respect to time t, this population is changing. If the population is increasing, right? If population is increasing, then this rate is increasing. Death rate is increasing. So where alpha is the per capita death rate due to the natural attraction. Again, we have to divide. We divided this factor into two parts. One is the alpha. This is the natural death rate, and gamma. Gamma is the dependency or death on the population size. Means this alpha is the natural death rate, and this gamma is due to the size of the population. That's clear. And you can check if x goes to 0. If x goes to 0, if x is small, yeah, if x goes to 0, then what will be the death rate? Death rate will be equal to alpha. So as same as the previous one. As same as the previous one. And when the size of population increases, then this rate, effective rate, alpha plus gamma xt increases. That's clear. So now this effective death rate is alpha plus gamma xt. So if we put in the previous equation, this is because now this is alpha. Alpha in the previous equation is replaced by alpha plus gamma xt. So if you put, then that rate of death will become, because you are multiplying by alpha xt plus gamma, means you are multiplying simply in this factor by xt. Actually, so just replace in the previous equation alpha by this quantity, then you will find out this resulting model. That's clear. And if you same as take the r is equal to beta minus alpha growth rate, then our model will become this one. So this model is dx over dt equal to rx minus gamma x square. So this model is known as the logistic model, or we will discuss it. So what is the this is known as the uh, with limited capacity or with carrying capacity, or logistic model. So uh, what is the difference between this model and the previous model? Yes. So think it for some time. As in the as previous we have discussed all the models, right hand side was the linear independent. But here this term is non-linear. This term is non-linear. So this is a non-linear differential equation, because this term is non-linear in x, right? Because due to this term x square. So due to this term, so this differential equation is a non-linear differential equation. Right? If we assume, if we assume this equation can be written as, because what was the previous equation? Previous equation was this one, Rx minus gamma x square. If I take common this term Rx, if I take this term as a common, then this equation can be written as, means if you take this term common here, Rx here, so this term can be written as, if you take Rx common, so here will be 1 minus x, and if you take k is equal to ry gamma, it's clear? So previous equation was Rx minus, well, just check the previous term, Rx minus gamma x square, Rx minus gamma x square. If you take Rx common, if you take Rx common, then it will become 1 minus gamma by R and multiplied by x. So if you take gamma by R equal to K, and this is nothing else, this is known as the carrying capacity. This K is known as the carrying capacity. So our differential equation can be written as in this form. So previous equation can be written as in this format, where capital K is not, they have taken gamma by R, they have taken Ry gamma as K, right? R by gamma, so it will become 1 by. So this is K is nothing else, is given as this. So this K is known as the carrying capacity, and you can check what was the R. R was the uh, growth rate in terms of beta minus alpha, and what was the gamma? Gamma was the death rate due to the population. So it is known as the carrying capacity. And this differential equation, as I said before, this equation is known as logistic equation, or it is also referred as the limited growth model, or model with limited resources, or density dependent. Why density dependent? Because it is depending on the axis. And we consider only R and K are the positive, because we have considered all are the positive uh, parameters, means alpha, beta, gamma, so K will be again the positive. So this is, I think, clear. This model is known as the logistic equation, or sometimes it is known as the sigmoid as well. Why it is known as the sigmoid or logistic model? Because the sigmoid is S type. If you solve this type of differential equation, then you will get this type of curve, right? So if you, this is nothing else, this is the part of uh, this type of function, S type function, like this. It is not I guess corrected. So means this is x-axis, y-axis, S type shape of the curve is there. So that is known as the sigmoid. This is only a positive value because t is measured at for the time t is positive, so they have considered only this one. So this is the sigmoid type function or logistic function or limited resource function, and you can check this is the time from 0 to infinity or any large t. Then, and what is this? This is the initial population x naught, and this is the k. Then our population will reach up to this level, and at this level then population will reach the constant. So this is known as the latent capacity. So there are some interpretation of the parameters. So what we will we can check how will you get this type of curve in solving this type of differential equation. So for this, I can show you the code. I have written a simple code in MATLAB for to simulate this. So suppose I explain it little bit. Suppose what is our equation? So our mathematical equation or differential equation is given as this r into x into 1 minus x by k, where r and k are the parameters. So I have defined as the parameters r and k. Actually, what is the global? Because there are two different functions. This is one function, this is another function, and this function is used in the this function. So actually I have defined these variables r and k here. So doesn't matter, you can define it here as well, and you can give the value here. Otherwise, if you define it here, so then if you make the global variable, so global variable means they can call from this function as well or this function. So otherwise, you can define it here as well, no problem. So you can give the value of r and you can give the value of k here. So I have defined it as a global. So these are the function name, logistic model, and this is the name of the function. Here is the RHS, right? So, and this is the returning value. Actually, a function, what is the function? Mathematical function. Function always takes some input and it gives you some outputs. So these are some inputs. X, t and x are as a input, and this is the name of the function, and it returns the value x dot, right? So x dot, what is it returning? It returning a differential equation type, means right hand side you have to write down like this, and you can give any name which is written in the left hand side, and that is written here. So that will be the returning value. So you can call this function here, and this is a very defined function OD45, which used to solve in MATLAB to an ordinary differential equation. Right? In mathematical, we use the DSolve. Here we use the ODE, and you have to define some values. And R I have taken 1, and K I have taken 1000. And what is the X naught? X naught is the initial value. Suppose I take 100. If I take 100, and what is the t end? T end is a, suppose I have taken the time in which I have to simulate. So 0 to t end means 0 to 15 will be the range for time. And what is the at the rate RHS? At the rate RHS is this function, means we have given this differential equation. If it is a system of differential equations, so you can write down so many differential equations here. So you can write any number of equations here, doesn't matter. And it always return, this function always return two components. One is for the t, and I have written as a t solve, and other one is the u solve, means it always return two vectors. In one vector, first vector, it always return the time, and in the second vector it returns the solution which is solved by the this function. So I have plotted this t solve and u solve. You can give any name here, right? So t solve versus u solve means x and y. This is the command for plotting. and K for the color here. So black color will be there. If you remove it, doesn't matter because it always by default gives the K. If I run this program, so before running it, I have to save it. So I write down the this is logistic simple model. You can give any name here, save and run it. So if I run it, then this is the uh, actually by default it is giving the blue curve. If you want to change the color, then you can write it as a black or red or something. So you can check this is the curve initially. What is the concentration? Sorry, population was the 100, and from 100 to this it is approaching to the 1000. It is will remain as the constant. Actually they have shown so many curve lines in this figure. Means this is only single. Okay, this is the single. So K will uh, K is the carrying capacity here. So I have taken the K here as a carrying capacity 1000. If I change, then that will change. So this was the simple simulation. So now we discuss some interpretation of the parameters. So in this differential equation, if I compare this differential equation as by the simple model, what was the simple model? Simple model exponential model was dx over dt is equal to r into x. So here, x is this one. So remaining term, what is the remaining term? Remaining term is r into this remaining term, this one, and this one. This one term is known as the this Rx, capital Rx. So this Rx is nothing else. This Rx is R and multiplied by 1 minus xy k. If you compare by the simple mode. Now we check this R. So what is this capital R? So this capital R is nothing else. This is the rate for this model. And how this rate is changing with respect to uh, time or with respect to x, we can check by this curve. Right here we have taken x on the x-axis and rx on the y-axis. Means we are checking how this rx is changing with respect to x. And what is the x? X is the population in the compartment. So if x is equal to k, if x is equal to k, if you put x is equal to k in this equation, then what will be the scenario? If you put x is equal to k, then this will become 1. So 1 minus 1 0. So rx will become 0. So at this point rx is 0. If x is 0, if x is 0, okay, second scenario, if x is 0, then this quantity will become 0. So 1 minus 0 is 1. So in that case, Rx will be smaller. So that will be the smaller. What is the smaller? This is the growth rate of the simple model. It means in this case, capital Rx will become the simply beta minus alpha. And between these points, from 0 to k, so you can check this is a straight line. Means if you want to find out the value of rx at this point, so value of this one, this one. So between this to this, so rx represent this type of statistic, this type of dynamics. So you can check means rx is uh, Rx is means rate is 0. It is 0 when the population in the compartment is X, and the rate is R when the compartment is 0. That's the original one. That's clear. So equilibrium, solution, and stability we will discuss in the next class. But first of all, I want to uh, explain little bit about means if I draw, or if I solve uh, this problem for different values of initial conditions. If initial condition is changed because x 100 is there, if I take x is equal to 200, then different curve you will get. If you take x naught is equal to something else, then you will get different curves. Means I have changed little bit, means I have changed this part only, means I have changed the initial conditions, and I have plotted many graphs and using the for loop. Means this code is put it in a for loop, right? I is equal to I 1 to length of x0. What is the x0? X0 I have taken, means 100 to 1500, and this is linspace, a command which creates a sequence. This is the starting point, this is the end point, and these are the number of points. Means break 100 to 1500 in 15 points. So it will create a sequence 100, 200, 300 up to 1500. That's clear. So I have taken a length of x naught. Length of x naught means it gives you the 15, because what will be the length means number of points here are the 15. And this is a for loop technique. For, this is the syntax to write down. For I is an index from 1 to length x naught. So length of x naught is 15. So 1 to 15. So this loop uh, um, will be executed 15 times, and I have plotted, means it will solve the differential equation for 15 times, and I have take x naught I, means if I is equal to 1, then it will take x naught I 1. X naught I 1 means the first element will be the 100. So it will solve differential equation. It will plot the first curve. Then if it will goes, then I will become 2. Then x naught I2 will become 200. Then it will plot again. And this command is the hold on. Hold on means to plot the curve on the same figure. So all other code are the same. If I run this program, so then you will get the 15 curves here. So 15 curves are here, but initially these are started from here. Means if x naught is 100, then after some time, then it will reach to this k. If x is 200, then again it is starting from 200 and is going to like this, and then will approach to this one. So if you start with different initial condition, then you are approaching to this solution. Means you are approaching at k, right? So what is this scenario? This scenario means this point, this type of point is known as the equilibrium point. Means if you start with different initial condition, but finally your solution are reaching to that particular point or particular solution, then that solution is known as the equilibrium point or equilibrium solution. So analytically, we will discuss what are the equilibrium points and whether it is a stable or unstable point. So we will discuss it next class. So now we continue some what will be the analytical solution for this type of differential equation. Means for logistic equation, what will be the analytical solution? So if you solve the logistic equation analytically, so I have already shown you this figure. So what will be the analytical solution of this differential equation? So I think it is not difficult to solve. Actually, this is a nonlinear differential equation, but by the way, this is a separable equation, right? Otherwise, it is not easy to solve. So it is a separable equation, so we can write it as like this. Means left hand side can be written as means this factor can be taken as this side, this whole factor is taken as the left hand side, so it will become k by x, k minus x dx over dt is equal to r. So r dt will be the right hand side and left hand side is this one. So we can integrate this if we can write it as a partial fraction. So it is a 12th standard problem. Okay, you can write this as k by x, k minus x can be written as in this form using the partial fraction, right? If you take the LCM, then you will get the same equation. x into k minus x, then k minus x will be there, plus x is there, so x will cancel out, so k upon x k minus. If you get this expression, then you can put it here in the left hand side in this format. So resulting problem will be this, and you can integrate both sides with respect to x now easily. Then this is will become the ln x, and it will become the uh, minus sign is there because minus x is there, so minus ln k minus x. Right hand side will become the rt plus c, and to find out the value of c, initial condition is given. So what is the initial condition? Initial condition is given that uh, x at time t is equal to 0 is x now. So if this condition is given, then you can find out the value of C1 easily, and the value of C1 is e to the power C. Okay, if you take the anti-log of both sides, then it will raise to the e to the power something. So if you put the value of C1 here, then and if you apply, then you will get this resulting solution. So this is the case when we have considered it when x is less than k, and if you take if x is greater than k, then that will become the negative, and in that case you will get the again same solution, so you can verify. So we have discussed the analytical solution for this one. So next class we will discuss the uh, stability analysis for this model. So we stop here and we will continue our discussion in the next lecture. Thank you.